So the topic for today is BPP, and
I don't think you're sharing screen.
I'm not sharing screen. My apologies. All right, do you see it now? Yeah, okay. So BPP and where it lies with respect to other classes.
I'll also just note, if you haven't begun recording, you can do that.
Oh yes, yeah, I started the recording, yes.
Okay.
So the first, so this is going to involve, some amount of probability theory. Nothing too fancy, but we'll be using probabilistic arguments here. So the first is a result of Adleman's theorem from 79 that shows BPP is in P/poly. And I like to think of the argument, sort of a quick punchline is basically hard coding the randomness. Okay, so let's prove Adleman's theorem. So what's the idea? So let's consider L in BPP and let Ln be the set of strings in L of length n. Okay, so that's Ln. And we need to construct a circuit Cn for Ln. And we also want Cn, the size of Cn. Cn should be of polynomial size. All right, so the key ingredient into all the theorems that we're proving today is we can use boosting to essentially make the probability of failure extremely small. So recall that since L is in BPP, there exists a polynomial time Turing machine M and a polynomial that I'll refer to as M of n, such that the probability over all R, where R is being chosen randomly, so that's what it, R is chosen randomly from 0, 1 to the M of n. So Mn is the length of the string. So the probability, so this polynomial Turing machine is M x R equal to L of x is at most, I'll say the probability of error, this is the probability of error, is at most, and I can make this sort of as small as I want. I can make it exponentially small. So I'm actually going to make it as small as 2 to the n, which I can do. Remember, I can make it exponentially small. And just to remind you, let me pull up my notes on BPP, the one that we had written, so that we can just go over that once again. Just to remind you here, we said that suppose we have a probabilistic polynomial time Turing machine where the probability of being correct was half plus inverse polynomial. So as long as it was even, let's say more than 2/3, we could get the probability that it's equal to be 1 minus 1 divided by 2 to the x to the d for any constant d. So we can get it down to 1 divided by 2 to the x. Right? I just said d is equal to 1. So I'm just saying the probability that they're equal is greater than 1 divided by 1 minus 1 divided by 2 to the x, to the length of x. And here I can just say the probability that they're not equal is less than 1 divided by 2 to the length of x, where again n is the length of the input x. I should say a probabilistic. Okay, so this is the main property that we have. And we'll see that just by using this property and using something called the union bound, we can easily find a way of hard coding the randomness. So what do I mean? So I'm going to call a random, or let me not call a string R in, so this is the random seed that is being fed. So call a string R bad for x if mxr is not equal to L of x. Okay? That's what it means for a random string to be bad for R. Bad for x. And the random string R to be bad for x. So what we have above is just saying that the probability that if you choose R random, the probability, so fix x, the probability that R is bad for x is at most 1 over 2 to the n. Okay, now let's look at this event. What is the probability over R that there exists an x? Remember, the x are all inputs of size n. We're only looking at inputs of size n because that's what we are focusing on for this language. We're just looking at the inputs of length n. So let's fix the inputs of length n. So I should say, x was of length n here. What is the probability that there exists an R such that R is bad for x? So one can write this basically as a union of events. The union over all x that R is bad for x. Remember, this is just an event. And we're looking at the probability of a union of events. Now we apply what's called the union bound. The union bound simply says the probability of two events A union B is at most the probability of A plus the probability of B. This seemingly simple fact appears over and over again in the analysis of probabilistic algorithms. If we apply the union bound here, we can replace the union by a sum. So we say the sum over all x, 0, 1 to the n, the probability that R is bad for x. But we just bounded this quantity over here. And this was by the definition of BPP and the boosting that we got. So we can say this is strictly less than the summation over all x and this probability, which is just 1 divided by 2 to the n. How many strings are there? At most 2 to the n. So this is 2 to the n divided by 2 to the n, which is 1. And there's a strictly less than here. What this is saying is, I'll put it all together, the probability over R, so you choose R at random, the probability that there exists an R that is bad for x, that probability is strictly less than 1. I'm going to write this out separately. So let's take some, and then we'll go back and look at it. So what it's saying is the probability over R that there exists an x such that R is bad for x is strictly less than 1. Okay? I'm just going to take the complement of this event. So now I can say the probability over R such that for all x 0, 1, R is good for x is strictly greater than 0. Now we apply what's called the probabilistic method. We're saying if the probability of some event is greater than 0, then there must be some situation where it happens. This implies, so now this implies, and this is called the probabilistic method, the probabilistic method. This is simply saying, since the probability is non-zero, there exists an R such that for all x, R is good for x. What does that mean? It means there exists an R, and just write down, which is some polynomial size, such that for all x out of length n, when R is good, that means that mxr is equal to L of x. And since we're only looking at things of length n, I can just say Ln. So it means there's this one random seed which happens to work for all the inputs of length n. There's one random seed that works for all the inputs of length n. We don't know how to find this. We don't know how to find this magic seed. So this is what I would call as like the magic seed. We don't know how to find the magic seed, but we know it exists. And as far as a circuit family is concerned, that is good enough. So now let me describe the circuit C of n. So the circuit C of n simply simulates or runs mxr, where the R is the magic seed. So you fix R. Now that we've discovered this R, the circuit, now this is the input now to the circuit, right? This is not the input. This is hard-coded. And the size of C of n is polynomial in the running time of mxr, which is polynomial in n. And so that ends the proof. So let me walk through this proof again. It's a bit of a, it takes some care. So let's go back. So we take some language in BPP. We look at all the strings of length n, and we call that script L of n. We need to construct a circuit for L of n of polynomial size. Okay, so since L is in BPP, we know that there is a probabilistic polynomial Turing machine and a polynomial mn. So mn is like the size of the seed. Mn is the size of the seed, the random seed, such that mxr is not equal to Lx, meaning that it makes an error with probability 1 divided by 2 to the n. At most 1 divided by 2 to the n, where n is the size, n is the length. So we have this probabilistic Turing machine whose error probabilities are exponentially small. And the fact that it's exponentially small is something we will exploit. Okay. Our aim is to find a random seed that happens to work for all strings of length n. the idea is to find a random seed that works for all. So suppose if we knew what this random seed was, suppose if we could find it in polynomial time, then we'd prove that BPP is equal to P, which is actually in some sense how these proofs on de-randomization kind of work. This is how you conjecture. If you could find some set of R's which are essentially going to be, so some of them are going to be good, then essentially you could just replace the randomness by that good seed. What we will argue is that there exists some string, and it's non-constructive. It just shows the existence, and that existence implies a circuit. We do not show how to actually, we don't show how to efficiently construct it. You can construct it sort of in exponential time. But we don't show an efficient construction of this magic seed. We show its existence. Okay, so, and in some sense, I say that it's non-constructive, although it is constructive, but in exponential time. Okay, so we'll call a string R. So when you look at a random seed, we'll call it bad for X if it gives the wrong output for that X. So for every X, there are a bunch of strings that are bad. Now, if you picked a random R, the probability that R is bad for X is at most 1 divided by 2 to the n. That's just a restatement of the BPP condition, of the condition of the Turing machine. Now let's analyze another event. What is the probability over R that there exists some X such that R is bad for X? What is the probability that there exists an X such that R is bad for X? This is like saying that you pick a string at random. What are the odds that it's a bad string for some X? If you fixed your X, we know that the probability that it's bad is 1 divided by 2 to the n. But the latter probability, the one that there exists, is likely to be quite high, because if you pick a string at random, there's probably some X for which it's bad. What we'll show is that this probability is strictly less than 1, which means there must be a string that is good for all X. And that is the hard code of the magic randomness. Now, how do we prove that this probability here, the probability that there exists an X such that R is bad for X, how do we prove this is at most 1? We apply the union bound. We say that the event over here is a union, can be expressed as a union of events. It's just the union over all X that R is bad for X, right? The event, you pick R and R is bad for X. This is an event. And we're looking at the union over all X. Now, by the union bound, we just say this is a sum over 2 to the n different events. There's a different event for each X. And there are 2 to the n of these events. So there's an exponentially large number of these events. On the other hand, the probability of each event is exponentially small. So they basically cancel out, and what you get is that the probability is at most 1. Strictly less than 1. So the probability over R that there exists an X such that R is bad for X is at most 1. Just writing that out over here. The probability over R that there exists an X such that R is bad for X is at most 1. Just taking the complement event, we know that the probability over R that for all X, R is good for X. This probability is strictly greater than 0. What this means is, if this probability is strictly greater than 0, there must exist an R for which this event happens. And what we get is there exists an R such that for all X, R is good for X. And so this is the magic seed. What this means is, if you plug this magic seed into the Turing machine, you will always get the right answer for all strings of length n. For all strings of length n, you are guaranteed to get the right answer. So then our circuit is simply just going to simulate on this hard-coded randomness. Remember, for a circuit, you just need to show the existence of the circuit. And so such a circuit exists. Right? And just to be formal over here, just to recall, how do we get the circuit? This is by the P in P/poly proof. Right? In that proof, we showed that any polynomial time Turing machine can be simulated by a polynomial size circuit family. And so that gives the circuit, and that ends the proof. Any questions?
I'm not entirely convinced that this shows the existence of a seed. To me, it shows that the existence of a seed can be, like, you can show that there's a very high probability of it existing, but doesn't necessarily, I don't necessarily see how that actually tells us that there definitely exists such a seed.
So think of this as, suppose it so happened that suppose this was not true. Right? So that means for every R, there exists an X such that R is bad for X. That would mean that if you picked an R at random, the probability that there exists an X, that must be 1. That probability must be 1. We're saying it's strictly less than 1. This is actually, I mean, even beyond this course, this is like a fundamental argument in combinatorics, and which is called the probabilistic method, which means you're trying to find a particular object, this magic seed. So what you do is you set up a distribution on all the objects, and you say, I'm going to pick an object at random and see what is the probability that it has magical properties. And if that probability is greater than 0, then I know there must exist something which has the magical property. It takes some getting used to. I mean, it's sort of a deceptively simple but deep concept.
I guess if for all, well, I guess that if it was not true that such a seed existed, then the requirement that most seeds should succeed would be. I'd need to think of.
Let me restate this argument in a different way, and you'll see that it's the same thing. Actually, I didn't want to state it this way, but I wanted to show you the probabilistic method. Let me restate this. And in some sense, probability, at least discrete probability, is really nothing but counting. Okay, let's actually not talk probability. I'm going to write the non-probabilistic proof here. So ignore the union bound. Okay. So we have this definition. Call a string R bad for X if this condition happens. Okay, first question. How many strings are bad for X? How many strings are bad for X? How many strings are bad for X? At most what? Anyone want to hazard a guess? By the way, by string, I'm thinking of strings of length mn, right? So what is the total number of strings of length mn? So it's like, what are the total number of options for the random seed? It's 2 to the mn. How many of those strings are bad? We said the probability is at most 1 divided by 2 to the n. So really the number of bad strings is at most 2 to the mn divided by 2 to the n. Is that logic clear?
For that part, yep.
Okay. Now let's go to the next step. We say, how many strings are bad for some X? So here you fixed X. I fixed x, and then I said how many strings are bad for x. That's how many. How many strings are bad for some x? Well, a trivial bound would be to say for each x, the number of bad strings is 2 to the mn divided by 2 to the n. The number of strings where a number of x's is 2 to the n. So they cancel out, and this is 2 to the m of n. Now there is a strict inequality here. So that how many strings are bad for some x is strictly less than 2 to the mn. Therefore, there must exist a string of length mn which is good for all x. And the probabilistic argument is identical to this.
See, yeah. And the 2 to the power of m over n divided by 2 to the power of n, like we can multiply that by 2 to the power of n, because that would be like the worst case scenario where all of them happen to be different.
Exactly.
And as well, for the first inequality we have that the number of them is less than 2 to the power of m of n divided by 2 to the power of n.
Yes.
If that was not the case, then it would fail the requirement in the definition of the language being in BPP.
Exactly.
That the probability is less than a particular amount.
Exactly.
Okay.
And I think you caught up on something. You said that this is the worst case when all of these sets were disjoint. The set being disjoint is like the events being disjoint, which is basically the worst case for the union bound.
Yeah. You can always use like best case, worst case scenarios to make inequalities work out nicely. Yeah.
Exactly. So this is the counting version. This is the probabilistic version. Why did I write the probabilistic version? Because we're going to be using the probabilistic version in the rest of the arguments today, in other theorems. But then this proves the existence of that magic string. The magic string is good for all x. So that means you get this magic seed, which is good for all x. I should have used seed as opposed to string there, but there's a magic seed that is good for all x, then you hard code that into the circuit. Okay, so this is the argument. And what this proves is that BPP is in P/poly. Okay, any questions?
Yeah. I think we touched on this on Monday, but BPP is starting to seem a lot like NP, right? Like this whole magic seed kind of seems like a certificate.
So that's interesting. Okay, good. So
I would kind of say on that it's like BPP. Most certificates work. Like if you randomly choose a certificate, it'll work most of the time. But for NP, you can choose to be really lucky with your certificate, like as in you can have it pick exactly the correct certificate.
But there's also the other side of it, which is that if it's not in the language, there is no certificate. Whereas here, if it's not in the language, there are still certificates. It's an issue of how many there are. So if you were to think of X as like a certificate, which is a good way to think about it, there are errors on both sides. That's why RP is in NP. RP says that if it's in the language, there are many certificates. And if it's not in the language, there's no certificate. But in BPP, you have error on both sides, which makes it tricky. Because again, going back to this, the reason why this random seed is not a certificate is because there's no way of checking whether the certificate is correct. We just know it exists. We don't know how to check if it's correct, so that gives a circuit family. It's not a verifier because you cannot check the certificate. And the same goes with the definition of BPP. There's really no way of checking the certificate. You can simply sample to count the number of certificates. And when you count, you can say, okay, I approximate the number of certificates, and based on that, I make a decision one way or the other. I mean, does that make sense?
Yeah. I can see it's not quite the same thing, but it's similar in a sense.
There is some feel for it, which is exactly why we're going to see. So this is leading on to our next theorem where we show that BPP, this is sort of suggesting BPP should be an NP. And if it's actually an NP, then it would be an NP intersection co-NP, because BPP is closed under complement. We don't know how to prove that. That would be a fantastic theorem to show. Instead, we can show that BPP is in sigma 2 by kind of getting this intuition that this is almost like some kind of a certificate, but then how do you check? And so this is what we're going to get to next. Any questions about this? Okay. So our next theorem, our next sort of big theorem that we'll prove, is a theorem of Sipser and Gacs, and this is it's sort of 82, 83. I say 82, 83 because I think Sipser had the first version, which was weaker. Gacs had a stronger version, which is proving that BPP is contained in sigma 2. And recall that BPP is equal to co-BPP. It's closed under complement, and hence BPP is actually in sigma 2 intersection type 2. So this is kind of saying, well, you want to say that BPP is an NP. We're not able to do that, so we have to stick an additional quantifier to make that happen. Okay, and the argument is it's a very clever argument. Okay, so what is the proof? So again, we'll start that L is in BPP. So there exists a probabilistic polynomial time Turing machine M and a polynomial M of n such that, as we discussed, the probability over R, so R is sampled uniformly at random over length mn size strings, mn length strings, that mxr is equal to L of x. This probability is at most 1 divided by 2 to the n, and remember n was the size of x, right? So this is for all x. For all x, this is true. And so again, the idea is to kind of look at these bad sets and good sets. So for x, define this is the set of good random seeds. So the set of seeds is essentially all R such that mxr accepts. So we have this notion of good and bad. Here we'll look at how many of the R's force it to accept. This is like counting the number of certificates. How many, although I don't want to use the word certificate, it's an abuse of notation, because certificate specifically refers to, things that can be verified. And here there's really no sense of verification. So it's another important distinction to be made. Okay, so let's define S of x. And for convenience, I'm just going to say m as opposed to m of n. So m is the length of the seed. Right? Here's the seed. That's the length of the seed, which I call m. And n is, of course, the length of the input. M could be larger than n. M is just some polynomial in n, the length of the seed. All right, so what we know is that if x is an L, then S of x, the size of S of x, is at least 1 minus 2 to the minus n times 2 to the m. This is the same argument sort of as before. So we know that there are the probability that it's wrong if x is an L, then the number of R which are going to make it accept, because that is the right decision, is a 1 minus 2 to the minus n fraction of all possible seeds, right? So this is the number of all seeds. If x is not in L, then S of x, actually I'll make this a strict inequality, is 2 to the minus n times 2 to the m, so which is really small. Okay, so I'm going to draw a cartoon picture for this, which, this picture is there in Aurora Barak, which I really like. And it kind of, I think, really gives the right visual picture that you should have to think about this. So think of this as the universe of all possible seeds. All 2 to the m seeds. This is S of x for x in the language. If you take something that is not in the language, this is S of x for x not in the language. This is actually even a bad cartoon picture. It's almost everything. Right? There's very little stuff outside. So these are the two cases to distinguish. Now, if S of x was actually everything, well, then you would start getting, then it starts to look like co-NP, right? Which is to say that when it's in the language, every setting works, and when it's not in the language, there are very few settings that make it work. And so what we're going to do is we're going to try to get that kind of an effect using quantification. Okay, so the trick used here is something. Okay, so any questions at this point? Does this cartoon picture make sense? Any questions? Right? Let's keep this cartoon picture here, and I'll just write the sizes here because that's going to be important. 1 minus 2 to the minus n times 2 to the m, and S of x is at most 2 to the minus n times 2 to the m. Okay, I'm going to now state two combinatorial claims, and I'm going to prove them later. We'll assume those claims, complete the proof that BPP is in sigma 2, and then we'll go back and prove those claims. So for that, I'm going to use this symbol as just the bitwise XOR. That's just the bitwise XOR. So I could take two strings, x and y, and this will give me a new string, right? This is just bitwise XOR. Okay, so consider a u in 0, 1 to the m. So that's another string in this set. And let u with S of x be the set, u bitwise XOR v for v in Sx. And this is called the shift by u. So we're shifting Sx by u. Okay, this is another set of strings. Note that the size of the shift is exactly the same as the original set. Right? So this is just taking every string and applying a bitwise XOR with a fixed string. So you fix u and you can do a bitwise XOR with everything. So that's like just shuffling. That's going to basically, if you did a bitwise XOR of Sx, you will basically shuffle it in the system. What we're going to argue that in this case, if you do a few shuffles, a few shifts, you can actually cover everything. Whereas in this case, with a few shifts, you cannot cover everything. And so this guarantee that you can cover everything versus you cannot, this is exactly what quantification and polynomial hierarchy will give us. Okay, I'm going to write down two claims here. So the claim 1, which basically says we can cover when x in L. And you'll see what this means. I'm just going to say if S of x has size 1 minus 2 to the minus n times 2 to the m. So Sx is really large. We're in this cartoon picture where it's extremely large. I'm going to fix a parameter k over here. I'll tell you what k is later on. So k is just going to be some polynomial in n. K is going to be fixed, and I will make it precise shortly. Actually, k, I can even write it down here. It's going to be 2 times m divided by n, which is just some polynomial. So it's going to be 2 times m divided by n. Okay, that's what k is. And you can, if m was smaller than n, then you just take the ceiling and you'll be fine. Or we can always assume that m is at least n. Just pad it with extra random bits so that it's at least of length n. All right. Then there exists u1, u2 up to uk, which are all elements in 0, 1 to the m, such that the union of all the shifts. So if I shift S of x by all the ui's, then I'm going to get all possible strings. So this is like saying if I shift, so there exists a polynomial number of ui's such that if I shift Sx by all these ui's, I will eventually get every string. I mean, you would hope that even maybe 2 shifts are enough. One would be the 0 shift and one is another shift, and that should be enough because it's almost all the strings. But we'll see that you need more shifts because you don't know what this set looks like. You don't know what S of x looks like. So the nice thing, it says as long as S of x has a particularly large size, then you can take a polynomial number of shifts and you will actually cover the entire set. Okay, that is saying we can cover when x is in L. Claim 2 says we cannot cover when x is not in L. So what this says is if Sx is less than 2 to the minus n times 2 to the m, if it's smaller, then for all strings u1 up to uk in 0, 1 to the m, for all strings, what we can prove is that the union of I going from 1 to k, ui plus sx, is a strict subset. Okay, this is strict. So this is now looking like a co-NP type view with shifting. Once you introduce some shifts, it looks like co-NP. And indeed, this is going to give sigma 2. So do these claims make sense? These are claims that are just about bit strings. They really have nothing to do with Turing machines. It's just saying you have some sufficiently large set, you can do a bunch of shifts, and you can cover the entire set of strings, the universe. Claim 2 says if your set is really small, then no matter how many times, no matter how you shift it, if you only do a polynomial number of shifts, then there's no way you'll cover every string. This is just a union bound. And if you think about it for a while, it's just a union bound. It's pretty simple to prove. Claim 1 is the hard one. Claim 1 is the challenging one. Any questions about what these claims are? So this is now helping us distinguish X and L from X not in L. Because the condition given in claim 1 is negated in claim 2. Right? So let me move on to the next page. I'll bring this back. Okay, so let's keep this. Let's keep this here. So let's assume the claims. I'll prove the claims later. But let's assume these claims, and then let's just go ahead and complete the proof that BPP is in sigma 2. I'll say X is in L if and only if. Just wanted to get the other one here. X is in L if and only if there exists U1 up to UK in 0, 1 to the M such that the union of UI plus SX, this is the entire set. Right? I mean, I'm just putting the claims together because we know that if X is in L, this condition is true. We know that if X is not in L, then the condition is false. Right? Because we just said then this would be a for all. And the fact is, the union of shifts is a strict subset. So this is what I conclude from claims 1 and 2. Okay, clear? All right. Okay, so I'm just going to use the double arrow sign now, just to show equivalence. Okay, so that is now equivalent just to saying there exists U1 up to UK in 0, 1 to the M such that for all Y in 0, 1 to the M, Y is an element of this union. I'm just rewriting this with another quantifier on Y. Okay, then let me go ahead and rewrite this yet again. I'll say there exists U1 up to UK in 0, 1 to the M such that for all Y, there exists, we'll see that this is not going to be, we're not going to need this quantifier. There exists I going from 1 to K. There exists an I less than K such that Y lies in UI plus SX. Okay. So far, so good. All right. Okay, there exists a U1 to UK such that for all Y, so I'm not going to write the sizes anymore because the sizes are all been fixed. Now here's the important point. Here's the critical point. Instead of writing Y being an element of the shift of UX, I can shift Y and check if it's in UX. So that's like saying there exists an IA such that ui XOR y lies in Sx. Now this is equivalent to there exists u1 up to uk such that for all y. Now what does this mean? This means that ui XOR y is a good seed, is an accepting seed, not a good seed, I'm sorry, is an accepting seed. Recall the definition of Sx is all seeds that makes mxr accept. Is all r such that mxr accepts. What this would mean is that there exists an I going from 1 to k such that mx ui plus y accepts. This is just a polynomial time machine. Right? This is just a polynomial time computation. It's simply a polynomial time computation. Right? Because k is just m divided by n. So this is just polynomial time. So there exists a ui to uk such that for all y, we can essentially run a polynomial time computation and accept, and determine acceptance or rejection. So x is an L if and only if there exists u1 to uk such that for all y, there is a polynomial time computation that accepts. Hence, the language is in sigma 2. Any questions about this?
Because sigma 2, QBF is about has to be a SAT formula at the very end of that. But I suppose that we can just, because that's a polytime computation, then, and obviously, SAT is NP complete, and that we can just convert that to a SAT formula, right?
Which what's over here?
Right.
This is not even a SAT form. This is like, once you quantify up to here, you're specifying u1 to uk and you're specifying y. So these are all fixed, and so all you have to do is run this machine. So it's not even SAT. This is in P. This is in P. Or this is a bad way of putting it. But whatever is happening in here is just a polynomial time computation.
Right, but for QBF, right, isn't QBF defined as as there being a Boolean formula that has to be satisfied?
Okay, so if you recall that there are multiple definitions, why you recall that there were multiple definitions of the polynomial hierarchy. One of them just had a polynomial time computation.
Oh, right. That's right.
You're right that if you wanted to convert that to a formula, you can, but you don't need to even do Cook-Levin to get it there exists. This is a deterministic computation. So there'll actually just be, it'll just be exact, you can just write out, so let me be, because it's a deterministic computation, you don't even need a quantifier, right?
Right.
Like you could just put down, you can represent the polynomial time computation by a formula. Indeed, the proof that P is in P/poly does that, right? It converts a polynomial time running into a circuit, which is also a formula.
Yeah, that makes sense.
But yeah, like there are multiple definitions of the polynomial hierarchy, so I'm using the one with polynomial time computation.
Gotcha.
So that proves that L is in sigma 2. I haven't told you the magic, which is how do you prove those claims. And we can do that. But first I want you to understand that that's how you prove that L is in sigma 2. Any questions? All right. Now let's go ahead and prove claim 1. So this is claim 1. And if S of x is large, then there exists u1 to uk such that all the shifts, the union of the shifts, will cover everything. And this is going to be sort of a clever probabilistic proof. Okay, so I'm now going to write the proof of claim 1. So we want to show the existence of u1 to uk. And we'll use the probabilistic method. So again, what we'll do is we'll just actually choose u1 to uk uniformly at random, prove that the probability of satisfying the condition is strictly greater than 0, which means the u1 to uk exist. So the way this will work is we pick u1, u2 to uk in 0, 1 to the m, I should say independently, and uniformly at random. So what is the probability? We'll say what is the probability, and we will show that the probability that the union of I going from 1 to k, ui shifted by this side, the probability that the union of these shifts, the probability that it actually covers everything, this probability will be strictly greater than 0. This is what we will show, and then we'll be done. Then we'll be done by the probabilistic method, right? Because then the probabilistic method will tell us that we're done, because we know that that means there must exist a u1 to uk such that this happens, and this probability is over u1 to uk. Okay, so again, taking the complement, we will show that this is just equivalent to showing that the probability over u1 to uk, that the union is not equal to 0, 1 to the m. This is going to be strictly smaller than 1. This is going to be strictly smaller than 1. And again, I'm going to write this out by showing that the probability u1 to uk, that there exists a y in that such that y is not in the union of all the shifts. But this probability is at most 1. Right, this is just the probability that there exists a y such that y doesn't lie in the shifts. I'm going to prove that this is, this is less than 1. So call this event b of y. So we want to show the probability of u1 to uk, that there exists a y where this happens, which is just simply saying the union of all of these events. We want to show the probability of this union is at most 1. All right. We will prove by union bound. By the union bound. So what we will show is we will prove that the probability of u1 to uk, that the summation over all y, we'll show that this is at most 1. And by the union bound, we know that the sum is greater than the union. So we're going to prove that actually the sum of probabilities is at most 1. And this is going to be good enough. All right? Remember, y is in 0, 1 to the m. Okay, so now let's say, what is the probability what is the probability of u1 to uk of by? What is by? Just writing it out. Remember, by was the event that y was not in the union of the shifts. This is the probability that y is not in the union of the shifts. Okay, so this is the probability. So there are k events here. So we can think of these events, right? So what does this mean? This means that this event, y is not in, this is s of x. Sorry, this should all be, my apologies, should be s of x. S of x. S sub x. S sub x. Okay. So we want y should not be in the shift of u1. Y should not be in the shift of u2. Y should not be in the shift of u3, so on and so forth. We want all these events to happen. Not one of them. We want all the events to happen, because if y is not present in the union, it is not present in any of the sets. So we actually want the intersection of all of these events. Y is not in the shift, the ui shift of Sx. We want all these, it's the intersection of all of these events, where each event is y is not present in the ui shift of Sx. Y is not present in the ui shift of the u1 shift, it's not present in the u2 shift, it's not present in the u3 shift, so on and so forth. These are all independent. These are independent events. These are independent events, because this is all chosen independently. And therefore, the probability of the intersection of independent events ends up being the product of probabilities. So now we get the product of I going from 1 to k, the probability over the choice of ui, that y is not in ui plus XORed with S of x. Now I'm going to take this. I'm going to XOR with UI on both sides, which is the same thing as saying UI XOR with Y is not in S of X. Now I'm going to XOR with Y, which is now saying that UI is not in S of X XOR Y. I'm just saying that Y not being in the shift of UI is the same as UI not being in the shift by Y. So Y is not in the UI shift is the same as UI is not in the Y shift. And the reason this is easier to think about is because S of X is fixed with respect to the probabilities, Y is fixed with respect to the probabilities. And as we argued earlier, the size of this is at most, I'm sorry, this is this is at least 1 minus 2 to the minus n times m. Right, so Sx XOR Y is very large. So the probability that UI, which is chosen uniformly at random, does not lie in this set. This is now easy to analyze. So I is going from 1 to k. This is the probability over UI, that UI does not lie in the shift of Y. And this is the product I going from 1 to k. Now, each of these probabilities is at most, because the shift of Sx is basically going to be the size of Sx, which is extremely large. So the probability is actually 2 to the minus n. The probability is simply 1 minus this ratio. And this is now 2 to the minus n times k. And this is where k I set to be 2m over n. Actually, even m over n is good enough. M over n is good enough. When I plug this in, I get 2 to the minus minus n times 2m over n, which gives me 2 to the minus 2m, strictly less than 2 to the minus m. Okay, so after all of these calculations, what we get is that the probability of by, which is that y is not in the union of shifts, the probability of by is at most 2 to the minus m. There are only 2 to the m of these. So the summation over all y of the probability of by is at most the number of y's, which is 2 to the m, times each individual probability, which is 2 to the minus m, and this is 1. So the probability over the sum over y of the probability of by is at most is strictly less than 1, which means the probability of the union of the by's is strictly less than 1. But what was this event? This event was exactly that there exists a y such that y is not contained in the shifts. So the probability over all the u's of this event happening is strictly less than 1, which now goes back is just saying this is the probability that the union of the shifts is everything is strictly greater than 0, which means there exists a u under uk which satisfy this property. This proof is like a classic proof using the probabilistic method. It's a classic probabilistic method proof. Very, very common in combinatorics and theoretical computer science to have arguments of this form. Okay, any questions?
So we said earlier that that probabilistically speaking, UI shift SX is the same as UI shift Y being in SX, or you know what I'm saying?
This one,
right? And so that's because the size of S of X and S of X shift Y are the same. So from a probabilistic standpoint,
it's not even probabilistic here. It's just saying that you can take the XOR, like the XOR of something with itself cancels.
Right.
So if you're looking at Y being in the shift of X, what you could imagine is shift everything by UI. So take UI XOR Y is not contained in UI XOR SX, but UI XOR UI is just nothing, or is zero.
Okay.
So I'm using the fact that a string XORed with itself is all zeros.
Oh, sure.
So I'm just saying that you could XOR UI on both sides. You get rid of the UI here, and the UI appears there. Then you XOR with Y on both sides. The UI disappears from here and goes over there.
Oh, sure. Fair enough.
So it's just it has nothing to do with probability. It's about XOR.
Okay.
Yeah. This is a proof that you need to go back and probably look at a little more carefully to see what is going on here. But what this proves is really this is the end of the proof of claim 1. Claim 2, the proof is actually quite simple. I can even just write it down here. It's just saying that if you look at the size of this, the size of this is at most k times the size. Well, okay, this is just saying this is at most the size. This is also a union bound, really. Is at most the size of UI XOR SX, which we just argued that the shift doesn't change the size. So this is k times the size of SX. So k is 2m divided by n, and S of x is at most 2 to the minus n times 2 to the m. And so the point is m is just a polynomial in n. So this entire thing is smaller than 1. So this is strictly smaller than 2 to the m, which means that the union of all the shifts, the total size of that is strictly smaller than 2 to the m. So obviously it's a strict subset of all strings of length m. So the proof of claim 2 is just this piece of math here, where you just track the size, right? Which is also a union bound, really, but you can just write it out non-probabilistically, just in terms of the sizes of the sets. And so these arguments prove claims 1 and claims 2. Using claims 1 and claims 2, you would then we get a proof of the Sipser-Gacs theorem, which shows that BPP is in sigma 2, or BPP is in sigma 2 intersection pi 2, showing that it's in the polynomial hierarchy. So we don't get NP, we get sort of one order more than NP. And of course, the first argument that we did was that BPP is in P/poly. So that we're just at our last minute. So that ends the last lecture. And so this covers just about the first 7 chapters of Aurora Barak. I think ignoring maybe some of the there's a chapter on diagonalization which I didn't cover. And this hopefully gives you like a fairly respectable view of what complexity theory is.